So last time we had started talking about integer multiplication, and the point there is that when you multiply two numbers, whether they're binary numbers or decimal numbers, you're basically multiplying, you're doing a series of multiplications between two single digits. And those digits might be bits if it's binary representation, or digits if it's base 10. Okay, so when you look at the traditional way of multiplying two numbers, 213 by 426, whatever that happens to be, the number of single digit multiplications, the number of those in this case is going to be, well, if this, in this case it's what? What's the actual number? It's 9, yeah. 3 times 3. In general, if this is n digits and this is n digits, then, well, the number is actually n squared, which is certainly theta of n squared. Okay? Now, we want to develop a method that is significantly faster, at least asymptotically faster, as n gets large. We want a function whose worst case number of digital multiplications is significantly less than n squared. Okay, and what we started observing last time is that we can think of a number in two parts. So we have a high order n over 2 bits. Okay, and x is now going to be binary, so we're going to multiply binary numbers. But it's still, if you have two binary numbers that are being multiplied together, you still go one bit at a time and carry and all this stuff. It's the same idea that you would do in base 10 multiplication, except now it's just base 2. Okay, so again, if you had two n-bit numbers, the number of single-bit multiplications that you would do in the straightforward algorithm, the one you all learned in grade school, would still be n squared. So in binary, we want to beat that. Okay, so if we can think of x as x1, which are the high order n over 2 bits, and x0, which are the low order n over 2 bits. And therefore, x is just equal to x1 times 2 to the n over 2 plus x0. Okay? This 2 to the n over 2 is what shifts x1 effectively to those positions. Okay, so you could think of x1 as an n over 2 bit number that's sitting here in the low order bits. What happens when you multiply that by 2? They move over by one position and you get an extra 0 at the right hand. So let me just do that. Like that number times 2. What is that number times 2? You just add a 0 at this end. That's that number times 2. What's this number times 2? You're adding another 0. So I'm thinking of that essentially the same way as saying, well, x1, when you multiply by 0, it's being slid over by one position, by one bit, and you get a 0 in there. 2 bits, it's slid over two positions, and so on. And so when you multiply it by 2 to the n over 2, x1 moves over to here, and the trailing elements are all zeros. And then if you add to that x0, this is what x is equal to. So that's the logic behind this, this little fact. And if we want to multiply x times y, we're going to look at y in the same way. We're going to have a y1. So y1, y0, and y1 times 2 to the n over 2 plus y0. So we can think of x and y in that way. So far we haven't done anything, just expressed x and y in those terms. Okay. So, but in those terms, let's multiply x times y and see what we get. X times y is equal to x1 times y1 times 2 to the n plus, now you'll see why I put these in parentheses in a minute, x1 y0 plus x0 y1 times 2 to the n over 2 plus x0 y0. All I've done here is multiplied. I'm just multiplying x by y, thinking of x in this form and y in that form, and then doing the particular cross terms. Okay, so this looks like some multiplications. This is multiplications. So this is a multiplication of two numbers, but how many bits are they? How many bits is x1? It's n over 2 bits, and y0 is also n over 2 bits. So this is the multiplication of two n over 2 bit numbers. Okay. Similarly, this is a multiplication of two n over 2 bit numbers, and this is a multiplication of two n bit, and this is a multiplication. So we have 4 multiplications of n over 2 bit numbers up here. Now, somebody should object that it actually looks like we have more multiplication. We have more than 4 multiplications. It looks like we have 1, 2, 3, 4, 5, 6 multiplications. Okay? But I claim we actually only have 4 multiplications. Why is that? Yeah?
Because multiplying by 2 to the n, or n over 2, is just a shift.
Right, right. Because we want to think of this when you're multiplying by 2 to the n or 2 to the n over 2 or whatever. That's just a shift. That's what I was showing you over here. You take that number and you shift it that many times. Okay? So if we want, we can count shifts as well, but they're different than multiplications. And in fact, you can think of it as just a placement or a rewriting. If I have x1 times 2 to the n over 2, what that means is that the first bit in x1 should be rewritten here. The next bit should be rewritten there. I don't actually have to shift one place at a time. I know exactly where they're going to end up because that's what's in the exponent. It tells me, I mean, I can figure out from this exponent and how long x1 is where it's going to end up. Okay, so I can rewrite this in n over 2 bit rights. So we want to pay attention to that time for rewriting in this whole algorithm, but a rewrite is different than a multiplication. So this would take, because these are, when you multiply 2n over 2 bit numbers, what's the size number you get? How many bits in that? Is what? N bits, I think. Yeah, so anyway, this is just going to be a rewriting of n bits, and this is going to be a rewriting of n over 2. Why is that n over 2 and this is n? Oh, because this was the term, this is the term that came from the multiplying of 2 to the n over 2 times 2 to the n over 2. So we got a 2 to the n there. The cross products in x1 times y0, 2 to the n over 2 is just going to have the 2 to the n over 2. Okay. So we've got 4 multiplications of n over 2 bit numbers. So if we just do the analysis of bit multiplications, how many bit multiplications do we have if we do the multiplication this way? So we can think of this now looks like a kind of a divide and conquer, a recursive kind of divide and conquer way of doing integer multiplication. So we would, instead of multiplying x times y directly, we'd think of x and y this way, and then we'd have to do this multiplication and so on. So it gives you kind of a recursive description of how you could do the multiplications. Okay, so let's do a kind of analysis of the number of bit multiplications when doing x times y this recursive way. I guess I should have stopped and asked whether everybody sees that this is correct. Oh. I mean, if you believe that this way of writing x is correct and this way of y is correct, that's the cross product, and therefore if you figure out what x1 times y1 is and then do that shift and so on, this should give you x times y. Okay, how many bit operations, how many bit multiplications will we have when we do x times y this way? So we'll answer that by setting up a recurrence. Okay, let T of n denote the number of bit multiplications of two n-bit numbers. Okay. So what is that? What do we want here? T of n is equal to, well, here's a multiplication between two numbers that have n over 2 bits. Okay, and here's another one. So what's the first thing we'll want to put in here into this recurrence? Well, we've got 4 of those n over 2 bit multiplications. So 4 times t of n over 2. Okay. Well, okay. Cn. Where does Cn come from? Yeah, you can think of it as shifting. I guess that's where it comes from. Either that or I have to redefine what T of n is. If T of n is just the number of individual bit multiplications, then what confused me is where does Cn come from? It looks like 4Tn is enough. But you do actually, if you're thinking about the efficiency of this way of doing multiplications, then you probably should account for the additions that you're doing. Okay, so we're doing 1, 2, 3 additions. 3 is a constant number. Okay, bigger than 2, less than 4. But the main thing is it's not influenced by n. Right? We have 3 additions in here, not influenced by n. But when you add n-bit numbers together, that's a bit addition. Okay, n-bit additions. So you could say this Cn is for the bit additions, and then I have to reinterpret T of n. It's T of n is not just the number of bit multiplications; it's number of bit multiplications plus bit additions, which seems like a more honest thing to do anyway, to include both the multiplications and additions. Okay. And then you could also add in the shifts, because we're doing 3 shifts. Here's a shift, actually 2 shifts. Each shift, this shift is n bits. This shift is n over 2 bits. So, and there's only 2 of them. And again, it's the number of these shifts. Well, there are 2 of these shifts. This shifts n bits. This shifts n over 2. That's uninfluenced by n. the number, how much you're shifting is influenced by n, but the fact that there's only 2 of them is uninfluenced by n, so the total number of bits you're shifting is n. So even if it takes you 1 time unit for each bit shift, that's still under the n. And if you just think of it as a rewriting, then again, it's n individual bit rewrites. So the Cn is for everything other than the actual multiplications. But what else do we have to do in this algorithm other than the bit multiplications that should be taken into this term? Well, you have to divide up x and y into the x1, y, x1, x0. Okay, so somehow, you've got an n-bit number, and you've got to somehow grab the most significant n over 2 bits and the least significant n over 2 bits, and that can cost you some time too. But again, we're saying the time that takes you is going to be proportional to n. So even when we add in all of the operations and not just the multiplications, this seems like the right recurrence for this approach. All of the work to divide the numbers appropriately, to do the shifts, to do the additions, that's in the Cn term. And the 4tn over 2, that's because we're doing the 4 multiplications of n over 2-bit numbers. Okay? Okay, what's the solution to this? Okay, let me ask the meta question. If you don't know the solution to this, how do you find the solution to this? Yeah, either unwrapping or the master method, or yes, those are the 2 approaches that we're using in this class. Okay, is that what you said? Okay. All right, so, and then if you actually take out the cheat sheet and look in it, it should come out to, well, theta n squared. End of lecture. Okay, any questions? Okay, we made no progress, all right? And I did warn you, this is the way the book likes to proceed often, that you do what seems natural, what seems like a good approach, and then you recognize that, no, that didn't work out too well. We'll have to do something different. Okay, so when you solve this recurrence, it's a good exercise setting it up. It doesn't save you anything. In fact, because of the overhead, and it's a more complicated algorithm than just the straightforward multiplication, it probably would perform worse than the traditional kind of algorithm, 1 bit at a time. All right, so what we need is a new idea, and it's a trick. Now, maybe people who really understand this stuff more deeply, and there's a huge literature on these kinds of tricks, there may be some ideas behind them that are deeper than, here it is, see, it works. But I don't have that deep understanding of it. So for me, it's just a rabbit out of a hat that I can show you, and we can see how helpful it is. And as I said, there are lots of these kinds of tricks that some clever people, and there's a community of people who think of these things, have come up with. But here's the one in this context. So let's observe that x1 plus x0 times y. Oh, I'm going to run out of board space. Let me right over here. x1 plus x0 times y1 plus y0 is equal to x1 y1 plus x1 y0 plus x0 y1 plus x0 y0. Just doing the cross products. Nothing fancy here. Okay? And I put the parentheses there for a reason that I'll explain in a minute. But one thing I want to point out, that each one of these terms, there are 4 terms here, those are the terms that show up here as well, not surprisingly. I mean, here we're doing a cross product of that involves x1 and x0, y1 and y0. So you're going to see those same terms. So this is the sum of all those individual terms that we needed over here. And by the way, how many multiplications are needed in order to get this product? In order to get that sum. Sorry, that sum. Well, one multiplication, this is an addition. So we have x1 plus x0. That's an addition of two n-bit numbers. This is an addition of two n-bit numbers. And then we have a multiplication of two n-bit numbers. So just with one multiplication of two n-bit numbers, we get the sum of all the terms that we needed here. But getting the sum is pretty far from getting those individual terms. But that's part of the trick. Okay. So I put this in parentheses because this is the same term, call it star, that's in parentheses over here. x1, y0, x0, y1. Okay? That term is what's in parentheses over here. Okay? So if I get the whole sum with one multiplication, and then let's say I get this one, x1 times y1, somehow, and I get this one, x0, y0, right? How do I get this? Okay? x1, y0 plus x0, y1 is equal to this whole sum, this is equal to that, let me give this a name, p. It's equal to p minus x1, y1 minus x0, y0. Okay, right? The middle term here that's in parentheses is equal to that whole sum, which I'm calling p, minus the two outer terms, x1, y1 minus x0, y0. So this looks like one multiplication. This looks like one multiplication. And we can get the whole sum in one multiplication. So that's just three multiplications. Okay? Three multiplications, and then we can get the inner term that we need with a subtraction. This total, p, minus the two outer terms that we're getting in one multiplication each. Everybody see the idea? Okay, or the trick? The trick is that three multiplications with appropriate number of additions, three multiplications of n over 2-bit numbers with some additions and some subtractions gives you all of the terms that you need up here. You get the x1, y1, because I'm saying we're going to get that explicitly. You get the x0, y0, because we're going to get that explicitly. And you get the middle part because we get the sum of all the terms, and we're going to subtract off x1, y1, which we just said we're going to get, and subtract off x0, y0, which we're going to get explicitly. And that gives you the middle term. So now you have all the terms you need up here to then do x times y. But instead of doing 4 multiplications of n over 2 bits, we're just going to do 3. Okay, that's the trick and that's the key. Everybody has to see that point or you're not getting what's happening in this lecture. Any questions on that? Okay, well, let's do the analysis then. Okay, so again, T of n is going to be defined as the total number of operations, multiplications, and additions. that is needed if you want to multiply two n-bit numbers. So number of bit multiplications, bit adds. I should have just said plus, other like shifting and etc. And so what's this recurrence? It's what? N over 2 plus, just again, Cn. That's really the same kind of work as before. So now we have this recurrence, all right? How do you solve for Tn now? What's the approach? It's the same as before. You either unwrap and see it, or you look it up in the master method, and hopefully it's covered by the master method, which it is in this case. And I'll just tell you what the answer is. It's, big O of n log base 2 of 3. Log base 2 of 3 is just a number, okay? Log base 2 of 3, is that bigger or smaller than 2? It's smaller, because log base 2 of 4 is 2. Log base 2 of 3 is certainly going to be smaller than that. And it's close to 1.9. So this is big O n to the, 1.59. So n to the 1.59, which is this is considerably smaller, in this business, considerably smaller than 2. 1.59 is smaller than 2. And n to the 1.59 is a function that grows considerably slower than n squared. Okay? So this term, this function n to the 1.59 is little o. I introduced that last time, but I'm not sure it's in the book. Little o of n squared. N squared really grows faster and dominates the growth of n to the 1.59. And you can try to plot this out or program it and see what that growth rate is. And the constant involved in this method, the overhead, is not terribly severe. Sometimes you can get an algorithm that asymptotically is much faster than some other algorithm, but the overhead, what's hidden in the C, is very large, and so n has to be very large. Sometimes n has to be very large before the asymptotically faster algorithm is actually faster than the asymptotically slower. But here, what's in the overhead, the constant part, is not particularly large, and so this way of multiplying two n-bit numbers really should do fewer total operations than the straightforward way for n fairly small. Okay, and you can try to work out exactly where that crossover occurs. Now, is it actually faster in practice? Then you'd probably have to get into questions of architecture and what's happening when you really do multiplications versus additions and all of that stuff. But at the algorithm level, when we're just looking at total number of operations, this way of doing it is definitely faster, and by enough that's probably going to overcome any disadvantages in architecture or advantages in architecture that the other method has. So this is a win, and it's supposed to be surprising that if you think creatively or differently about something which is a very natural kind of operation, multiplying integer numbers, you can actually get something that's quite different and has different properties, complexity properties and time properties than what you're used to. And people have thought this way, very impressive results in matrix multiplication and similar kinds of ideas, but more complex. And we don't do it in this class, but often we'll do that in the graduate version of this class. So matrix multiplication, if you think about multiplying two, let's just say square matrices, n by n two n by n matrices, how many scalar individual multiplications do you do? In the traditional way of multiplying matrices. N what? N cubed, yes. Because we have n individual numbers in each row, and each row is multiplied by each column. So this is multiplied by that, this is multiplied by that, and so on. So for each row and each column, you end up with n individual multiplications and then n minus 1 additions. And you have n rows, n columns, so n squared combinations of rows and columns. So n squared combinations of rows and columns, each one requiring n individual scalar multiplications. That's n cubed overall. So n cubed scalar mults for sort of the definition of matrix multiplication. But with similar kinds of ideas, but more complicated tricks, the tricks in matrix multiplication are more involved, but similar kind of style of thinking. People have gotten more and more complex algorithms, more and more complex tricks to get the from theta n squared down to, I'm not sure where they are now. I think it's like 1.2, somewhere in that range. I'm sorry, n cubed 2.2, sorry. So this keeps coming down and down and down, and they work for bigger and bigger n. I mean, the size n, the size of matrix you have to go to before the next one is better than the previous one gets bigger and bigger. So I think this one, whatever the fastest is, whatever the smallest is, only becomes advantageous for n in hundreds of thousands or something like that. But there's a huge, or there was at least a huge body of research that people did in trying to improve those kinds of results. Okay, so that's that for integer multiplication and this kind of divide and conquer. What I want to do next is, I guess you could think of it as divide and conquer too, but it's a little bit different, and particularly because the main point in the analysis that we're going to do is to do a little bit of randomized analysis, a little bit of looking at algorithms that are not deterministic. Okay, because oftentimes in algorithms it's very advantageous to have some randomness in there, to have a non-deterministic algorithm. And so what we're going to talk about is a randomized version of quicksort, and in particular analysis of the expected running time of that algorithm. Now this is in the book, I think in chapter 15 or so. We're going to expand a little bit on what's in the book, because the book assumes that you've already had a reasonably good background in probability. And I know that probability is not a requirement, is not a prerequisite for this class. So how many people actually have taken a course that's had a fair amount of probability in it? Okay, some. And how many have not? And some. Okay, so sum plus sum adds up to less than a whole. There are some people who didn't answer. Well, I'm going to defer the discussions of probability, and according to my notes, I have some notes on this that I can post on the web. I'll search for them. But I'm going to talk first about quicksort, and in sort of a general context, and then we'll see how to add in the randomized elements and the randomized analysis. Okay, so actually I'm not starting with quicksort, I'm starting with well, an algorithm called select. Okay, so this is going to be a recursive algorithm. Select Sk, where S is a set of numbers. And just for convenience, we'll say that they're distinct. There are no ties. They're distinct numbers. Okay? And we want to find the kth smallest. Kth smallest number in S. Okay? So that's what select Sk, this is a function of S and K, which will return the kth smallest number in S. So if I say S1, that's the smallest number in S. And if I have S and K is the size of S, that's the largest number in S. And if I have S and roughly half the size of S as a value of K, that's the median, right, of the set S. So this is a function that has some versatility. It's a range of numbers that it can return. And we think of this as a procedure heading as well as a function. So this is sort of the beginning of the algorithm description. So here's the algorithm. Well, that's, or I'll rewrite it. The header, select Sk, and the algorithm is pick a number AI, I'll call AI, it's contained in S. And this number is called a splitter. Okay? Now, how you pick this is going to be the subject of interest. You can pick it, if you pick it in a deterministic way, let's say you picked the first number in your representation of S. That's deterministic. Or you can take the last number in the representation of S. That's deterministic. But if you pick it randomly from your set S, S is represented somewhere in memory, and so you could pick a random memory location and take that randomly, then the behavior of the algorithm could be different than the behavior when it's always deterministic. Okay, so later we'll specify how we're going to pick that splitter, but for the time being it won't matter. Just pick one. And S minus, it's the set of elements, numbers, in S that are strictly less than AI. Okay? And S plus, those are the elements that are strictly bigger than AI. Okay? Why is nothing equal to AI? Oh. Actually, it could be, right, because I didn't say you removed AI from S. So, yeah, okay, I confused myself. It's just that we don't care. Okay, we've got AI in our hands, and all the numbers are distinct, so all that remains of interest are the ones that are less than AI and the ones that are larger than AI. But so logically, why we didn't include the possibility of equal is that AI is the only one that's equal to AI. Okay? All right. Now, if the size of S minus is equal to K minus 1, what can we conclude? So S minus, those are the guys that are strictly less than AI. And we're looking for the kth smallest element in S. So we can conclude that AI is the kth smallest element, because exactly K minus 1 are smaller, and all the other ones are strictly bigger than AI. So AI must be the kth smallest, and so we'll return AI. Okay? If S minus is greater than or equal to K, what should we do? So the number of elements that are strictly less than AI is greater than or equal to K. We're looking for the kth smallest element. So where is the kth smallest element? It's not AI, because this would have to occur for it to be AI. Is it in S plus? No, it's got to be an S minus. So in that case, what we're going to do is we're going to call select on S minus. That's the set we know it's in. And what are we looking for? We're still looking for the kth smallest. Okay, so this is a recursive call to select, but the set we're giving it is smaller, so we're making some progress. All right. Third possibility, S minus is equal to L, that's just for notation, where that's strictly less than K minus 1. Okay, so we had S minus was equal to K minus 1, S minus greater than or equal to K. The only possibility left is that the size of S minus is strictly less than K minus 1. Then where is the kth smallest element? It's in S plus. So in that case, we're going to make another recursive call to select, this time S plus. And what element are we looking for in S plus? Yeah, do we want the kth smallest in S plus? No, because we already know that S minus has some size, and the kth smallest is not in there. So we want now, for the kth smallest, it's K minus 1 minus L. Now, I'm always confused about plus or minus 1. And when it gets to programs, I always have to test it out, or I have to count on my finger. How many people think it's K minus 1 minus L? How many people think it's K minus L? And how many people think it's K minus L plus 1 or something else? Okay, well, figure it out at home. It's one or the other. It's either K minus L or K minus 1 minus L. But you see the logic of it, okay? Oh, it's K minus 1 minus L, of course, because there are L that are too small in S minus, and AI is too small. That's where the extra 1 comes from. And, yeah, so it's K, which is what we're looking for, minus L minus 1. Right. Okay, so that is right. And we make that recursive call. I guess we need a base case here. If the size of S is equal to 1, return. But otherwise, we do this. So, does everybody see the recursion? The recursion in this, and this is a correct algorithm, modulo little programming details. A correct algorithm that should find the kth smallest in the set S. Okay? Now, what is the worst case running time of this algorithm? Let's do a recurrence relation analysis. Tn is equal to what?
What's n?
N? Oh, so n is the size of S. Okay, so you have a set that has n elements. What's the worst case running time? Well, what's the worst case kind of thing that can happen here? Where are you making very little progress? what?
It's either in S minus or S plus.
Well, okay, the suggestion was it's when it's either an S minus or S plus. Certainly, the other possibility that is that you found it at this moment, that's the best thing that can happen. Okay? But what's the worst is, yes, it's true that it's when one of these other two things happen, but which one in particular? Yeah.
Well, if you keep selecting A1 as either the smallest element in the at an S.
Yeah, it could happen that what you select, A1, is always the smallest. What happens if it's always the biggest? If A1 is always... Let me use that one, because that's clearer to me. I don't know why. You're probably right. But if A1 is always the biggest that's in the set that's remaining, okay, then you're just successively calling select on S minus with K until finally you get down to where S is small enough. Okay, somewhere, some base case. Okay, but the point is, you could just be, the progress you're making at each call could just be getting rid of one element. That's the worst thing that could be happening, that all you're doing is recognizing that AI is not the element you want, and you're getting rid of it, but other than that, you're not making any progress at all. So this is T of n minus 1 plus the work you actually had to do to get there. And what are you doing to get there? You're picking a splitter. Well, that took only constant work, but now you're figuring out S minus and S plus. How do you figure out S minus and S plus? You're explicitly comparing AI to all the other elements. So this is Cn. Okay, that's for the comparisons. And what does this solve to? Well, you have n operations the first time, n minus 1 the second time, n minus 2 the third time. Add those up and you get what? 1 plus 2 plus 3 up to n is equal to? N, well, something like theta n squared, right? N times n plus 1 divided by 2. Okay, so the worst case running time of this is not very good. And next time what we'll do is we'll be picking the splitter randomly. We'll do analysis of the expected time that takes, and I'll have to explain what expected means in this context. And then we'll go on to quicksort and do randomized quicksort.